Hello everyone, welcome to my channel. This is an educational channel. We focus on theories of everything, all encompassing theories, cosmologies, paradigm shifters, and anything else that we think you might not know about, but you'd be happy if you did. Today is our 421st video that we've done on the reciprocal system of theory. And the reciprocal system of theory was originated by Dewey B. Larson. Back in the 20th century, about 1959, he proposed his two fundamental postulates, just two sentences about how he believed the universe operated. And then he took those two postulates and through a process of deduction, kind of an if this then that approach, he derived a theoretical universe, what my universe would look like if my postulates were correct. So he has a theoretical universe, and then in many of his books, he compares his theoretical universe with the so-called actual or measured universe of the legacy scientists. And he does that in this book here that we're looking at called Basic Properties of Matter. This is a book on chemistry, looks at the periodic table and the elements and compounds in the periodic table, and Larson derives equations for some of the different basic properties of matter, such as the melting point or the specific heat or the compressibility, or in the case of this chapter, the inter-atomic distance. And then he compares his values with those of the scientific tables that have been compiled by legacy chemists. And it's an interesting study. So we're going to get into chapter 2, but let's first kind of identify Larson's theory. The first postulate, the universe, is composed of one component entirely, one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, I try to focus mainly on the first postulate. The second postulate is just kind of like, not only is it disputed by some of his followers, the geometrical limitations of Euclidean geometry, but it's also just kind of axiomatic, like, 2 + 2 = 4. And if you don't accept that, then, you're not really, going to be able to follow this. And, so too, with the first postulate, the basic thing that you have to be able to accept in Larson's universe of motion, not matter, not energy, but motion, is the primary, the sole constituent of the universe. So you have to be able to accept the fact that motion exists before anything moving. You have to be able to recognize that in an empty universe, a universe with nothing in it, you still have motion. And Larson calls that the progression. And the progression is what he calls a scalar motion. This is a motion that you can envision with a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other. And but they won't be moving in any specific direction, or they'll be moving in all directions. So that is a scalar motion, a motion with a magnitude, but it has no specific direction. And then Larson calls that the progression. And then the opposite of that would be if you sucked in the balloon and the balloon contracted, then all of the dots would be moving toward each other. But again, they're not moving in any specific direction. That inward movement is analogous to gravitation. So those are the two main motions to start out with. The empty universe is basically composed of outward motion, what he calls the progression. He calls it the progression of the natural reference system when it is when it is specified as really like the default motion of the universe, which we'll derive here once we establish the space and time thing. So he says that the universe is made out of motion. Motion is the relationship between space and time. This becomes a generalized reciprocal relationship between space and time. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. And all forms of really scientific quantities are forms of motion. But as the postulates say, motion is in 3 dimensions, and so space and time come in 3 dimensions. Larson calls that coordinate space and coordinate time. XYZ coordinates in space in a still frame. Now this is a vectorial, so this is kind of an abstraction. This is once you kind of stop the universe in order to make measurements. Then you get vectorial motion where you can identify directions, and you get a still frame. But the frame of the progression of the natural reference system is in motion. The real universe is in motion. You can abstract space and time, but that is just really for the purposes of measurement. And so space and time have 3 dimensions. So when you make these scientific units, they're all different forms of motion. Fractions with space or time as the numerator, time or space as the denominator, but space or time can come in multiple dimensions. And so, you know, all of our scientific quantities, such as matter and energy, force, acceleration, momentum, pressure, power, these are all relationships between space and time. They are all fractions with space or time as the numerator, time or space as the denominator. Motion, speed, is the most basic form of motion we know of. The car is moving 15 miles per hour, 15 miles of space in 1 hour of time. That is space over time. Its reciprocal would be energy. Energy is time over space. It took me 30 minutes to push that thing half a mile. 30 minutes of space, 30 minutes of time in 1/2 hour of space. I'm sorry, 1/2 mile of space. And matter turns out to be time to the 3rd power over space to the 3rd power. And each one of the different qualities, scientific entities, units, has a space-time signature there. So we've got, you know, really 2 aspects here. We've got the vectorial motion and the scalar motion. And then we also have this discrete unit postulate. And that's basically saying that space, time, and motion come only in discrete units. You have to have a full unit. You know, you can't go and say, you know, go to the tree and pick me half an apple. No, you have to either pick a whole apple or no apple at all. Or you can pick 2 or 3, but you can't pick 2.5 or something like that. And space and time and motion are the same. They come only in whole units. Now, those units are very, very small. So, you know, practically, it's hard to measure smaller than a unit. But you do have to have a whole unit. And if you have exactly 1 unit of space in 1 unit of time, space over time being speed, you have what Larson calls unit speed, which is also known as the speed of light. So the speed of light is this 1/1. And if you know reciprocals, 1 is really at the center of the number line of reciprocals. You know, all reciprocals, when you multiply them together, they equal 1. So this 1 is the neutral point of the universe, the speed of light. And that's the progression, the speed of light outward in all directions. So, you know, you envision this expanding balloon moving out at the speed of light. That is the progression of the natural reference system, and that is the empty universe. That means that half of the universe is actually moving faster than the speed of light. Half is moving slower. Larson refers to these as the cosmic sector and the material sector, respectively, and they are reciprocals of one another. So in the material sector, which is really the only sector that legacy science knows of, and that's the sector that we, you know, live in and are familiar with, we have relations that are based on coordinate space, 3 dimensions of space in a still frame, and clock time. The clock is moving in a scalar manner, always getting later and later, or always moving farther and farther apart, but in no particular direction. You don't say that time is moving north or something like that. So in the material sector, you have coordinate space and clock time. But then when you cross that unit speed boundary, that speed of light boundary, then you move into the cosmic sector. And in the cosmic sector, you have relationships based on coordinate time and clock space. So you have 3 dimensions of time in a still frame, and you have space is always getting farther and farther and farther apart in the matter of dots on the expanding balloon. And so they are reciprocals of one another. So you can really, even though you know very little about what's going on in the cosmic sector, to a certain extent you can extrapolate what you know about the material sector into the cosmic sector. Now there are a few caveats that you have to keep in mind. But so also then within each one of those sectors, there is an inside region, inside a unit of space and inside a unit of time. Those two are also boundaries where when you cross those boundaries, the rules reverse. And so within the material sector, if the interactions are occurring within 1 unit of space, which is 4.56 times 10 to the minus 8 meters, then you don't have space because you have to have a full unit of space. So if you don't have space, that means you only have time, because the universe is composed of motion, which is the relationship between space and time only. And so it has to be one or the other or both. And so if it's not space, it has to be time. And so Larson refers to this as the time region. And this is the region of atomic interactions, molecular interactions, and a lot of our chemistry is going on here in this time region. But when you cross that unit space boundary and move into the time region, the directions reverse. So in the outward region of the material sector, the progression is moving everything farther and farther apart, and it is moving, and gravitation is moving everything closer and closer together. But within the time region, it is the opposite. The progression is moving things closer and closer and closer together, and gravitation is moving things farther and farther and farther apart. And within this time region, the progression is a constant. It is always moving at the speed of light. And gravitation is variable. It's based on this inverse square law. So there is a point within the time region where gravitation and the progression are equal. And that's what Larson calls the interatomic distance. So his equations are solving for where they are equal, the progression and gravitation. Okay, now let's start reading here from chapter 2. He's derived his equations, and he's kind of just in the weeds a little bit, just kind of talking about the specifics. He divides up the periodic table into 4 divisions, and several different rows. For Larson, the atom is based on a 3-number sequence. First, it starts out with 2 photons, which are motionless in the natural reference system. But you have 2 photons because they both will be photons are simple harmonic motions, wave-like motions. They can both be kind of superimposed on one another with the same center if they're at the same speed. And then those 2 photons are still moving outward with the progression. In order to slow them down and get them to gravitate, you have to rotate them in 3 dimensions. And so every atom has a primary 2-dimensional rotation, a secondary 2-dimensional rotation, and those 2 alternate one after the other. And then you have a 1-dimensional rotation in the opposite scalar direction, which can be positive or negative, and can actually be 0 also. If it's 0, then you're talking about the noble gases or the inert gases. So that is really, he uses those numbers and alters them a little bit by adding 1 for the specific rotation. And that's what he has to work with when he is determining the interatomic distance of each one of the elements. He's gone through several of the different kinds of elements so far that we've kind of compared the numbers that he derives with the numbers that the legacy scientists have found, and just about in every case he's at least within like 1% of the accepted value. In a couple cases, it gets up to 2 or 3%. He usually has some kind of explanation for that. Okay, the specific magnetic rotation of the 1b group, which includes only the 2 elements hydrogen and helium, and the 2a group of 8 elements beginning with lithium, combines the values 3 and 2, where the value 2 applies to the subordinate rotation. 1 dimension is inactive. Where it applies to the principal rotation, 2 dimensions are inactive. This reduces, so there in parentheses after those 2, the first one where it applies to 1 dimension inactive, he has 3-2, and where 2 dimensions are inactive, he has 2-3. Not quite deciphering that right now. This reduces the force exerted by each atom to 2/3 of the normal amount in the case of 1 inactive dimension, and to 1/3 for 2 inactive dimensions. The interatomic distance is proportional to the square root of the product of the 2 forces involved. Thus, the reduction in distance is also 1/3 per active dimension. That paragraph kind of lost me there, but maybe we'll figure it out as we move along. Since the electric rotation is not a basic motion, but a reverse rotation of the magnetic rotational system, the limitations to which the basic rotation is subject are not applicable. The electric rotation merely modifies the magnetic rotation, and the low value of the force integral for specific rotation 2 makes itself apparent by an interatomic distance which is greater than that which would prevail if there were no electric displacement at all, or unit-specific rotation. Theoretical values of the interatomic distances of the lower group elements are compared with measured values in Table 6. So here we're going with the lower group elements. And again, these measurements are all in angstroms. Hydrogen, calculated 0.70, observed 0.74. Helium, calculated 1.07, observed 1.09. Lithium, calculated 3.05, observed 3.03. Beryllium, calculated 2.28, observed 2.28. Boron, calculated 1.68, observed 1.74. And in boron's other orientation, calculated at 2.11, observed at 2.03. So those boron calculations are a bit off. Carbon, the diamond form is 1.54 and observed at 1.54. The graphite form is 1.41, observed at 1.42. And then there's a form also that is a different orientation, 3.21, observed way up at 3.40. And nitrogen also calculated at 1.06, observed at 1.06, but the other orientation calculated at 3.21 and observed way up at 3.44. Oxygen 1.06, observed 1.15. Other orientation 3.21, observed at 3.20. And fluorine calculated at 1.41, observed at 1.44. So there's usually when he's dealing with the lower group elements, there are more anomalies there, and he is subject to make more mistakes usually with the lowest groups. The figures in parentheses in column 4 of this table indicate the effective number of dimensions. Thus, the rotation 3 parentheses 1 shown for hydrogen means that this element has a specific magnetic rotation of 3 effective in only one dimension. Except where the crystals are isometric, there is still much uncertainty in the distance measurements on these lower group elements, and many other values have been reported in addition to those included in the table. This situation will be discussed at length in Chapter 3, next chapter, where we will have the benefit of measurements of the distances between the atoms that are constituents of chemical compounds. As indicated in the introductory paragraphs of this chapter, we are not yet in a position where we can determine specifically just what the interatomic distance will be for any given element under a given set of conditions. The theoretical considerations that have been discussed actually do lead to specific values in many cases, but in other instances there is an uncertainty as to which of 2 or more theoretically possible rotational arrangements corresponds to the observed crystal structure. Continuing progress is being made in both the experimental and the theoretical fields, and it can be expected that these uncertainties will gradually diminish toward the irreducible minimum that was mentioned earlier. In the course of this process, there will necessarily be some changes in the identifications of the observed interatomic distances with the theoretically possible structures. A comparison of tables 1 to 6 with the corresponding tabulations of the first edition should therefore be of interest as an indication of the nature and magnitude of the changes that have taken place in our view of this interatomic distance situation in the last 20 years. and by extension, an indication of the amount of change that can be expected in the future. Such a comparison shows that the modifications of the original conclusions that now appear to be required in the light of the additional information that has been made available are confined almost entirely to those which have resulted from a better theoretical understanding of the behavior of the specific magnetic motion above an effective value of 4. Few changes are required in either the magnetic or electric values in those rotational combinations where the specific magnetic rotation is 4-4 or less. One of the puzzling features of the rotational situation as it appeared at the time of the original publication was the apparent retrograde progression of the specific magnetic rotation in groups 4A and 4B. It was recognized that at that time that both the 4.5 and 5 values for the specific rotation correspond to the same displacement, 4. The difference being that in the case of the 4.5 value, the rotation extends to 2 units of the vibration, and the last increment of specific rotation in this case is only half size. The next half unit increment, if such an increment were possible, would bring the 4.5 rotation back to the 5 value. It would therefore appear that the sequence of specific rotations beyond 4.5-4 should be 4.5-4.5, 5-4.5, 5-5, and so on. But the tendency is in the opposite direction. Instead of moving toward higher values as the atomic number increases, there is actually a decreasing trend. This was already evident at the time of publication of the first edition. That first edition came out in 1959. This book, Basic Properties of Matter, is from 1987. As the low interatomic distances of the series of elements from tungsten to platinum could not be accounted for unless the specific magnetic rotation dropped back to 4-4.5 from the higher levels of the preceding elements of the 4A group. This decreasing trend has become even more prominent as distances have become available for additional elements of group 4B, as some of these values indicate specific magnetic rotations of 4-4 or possibly even 4-3.5. As it happens, the continuation of the trend toward lower values in the more recent data has had the effect of clarifying the situation. It is now evident that the 5-5 specific rotation is not reached within the accessible portion of groups 4A and 4B. Considerations that will be discussed later show that the specific rotation of 5-5 would be unstable. The lower values in the 4A and 4B groups do not result from a decrease in the magnetic displacements, but from a shift of the existing displacement units from vibration 1 to vibration 2, a process which reduces the specific rotation of the units by 1/2. On a vibration 1 basis, rotational displacements 4-3 correspond to specific rotations 5-4. The conversion of successive units of displacement to vibration 2 without change in the number of displacement units results in a series of specific rotations 5-4, 4.5-4, 4-4.5, 4-4, and so on. A similar series with one additional displacement unit goes through the values of 5-4.5, 4.5-5, 4.5-4.5, and 4.5-4, and then follows the same route as the series with the lower displacement. The modifications that have been made in the theoretical rotational values applicable to the elements of these two highest rotational groups since the publication of the first edition are the result of a review of the situation in the light of this new understanding of the trend of the specific rotation. The general pattern in group 4A is now seen to be that of the series from 5-4.5 to 4-4.5, with a return to 4.5-4.5 in the lower electronegative elements. So far as can be determined at this time, group 4B follows the same pattern one step farther advanced. That is, it begins with 4.5-5 instead of 5-4.5. The difference in the interatomic distance corresponding to one of the steps in this conversion process is relatively small, and in view of the substantial variation in the experimental values, it has not appeared advisable to take into account the possibility of combinations such as 4.5-5 specific rotation of one atom of a pair and 4.5-4.5 in the other. It seems clear that such combinations do exist in some of the lower group elements, sodium, for example, and they probably play some part in the higher groups. Most of the reported distances for holmium and erbium, for instance, agree more closely with a combination of 5-4.5 and 4.5-5 than with either individually. However, all of these values are theoretically possible, and the only question at issue in this and many other similar cases in which theoretical value corresponds to the observed distance. Definitive answers to identification questions of this kind will have to wait until the theoretical probabilities are specifically evaluated on the experimental uncertainty, or the experimental uncertainties are resolved. Many questions concerning alternate crystal structures will also have to wait for more information from theory or experiment, particularly where crystal forms that exist only at high temperatures or pressures are involved. There is, however, a large body of information already available in this area, and it can be tied into the theoretical picture as soon as someone has the time and the inclination to undertake the task. Okay, that's the end of that chapter, chapter 2, interatomic distances. Now, chapter 3 is called distances and compounds. So here in chapter 3, he's going to be looking at the interatomic distance, but it's really going to be the intermolecular distance. And we'll start tackling that chapter tomorrow. Keep your head up and keep working. Just be a detective, and we'll see you tomorrow.